in one dimension. Suppose I know that at the initial point of time, this particle is at say x naught. So immediately I know that p of x comma 0 is delta x minus x naught. X comma t. That's how I define this p as a function. P of x comma t. P of x comma 0 is delta of x minus x naught. And why I do this, I later want to do something like Green's function sort of thing, and then we will realize that this starting with something like this will later give us the most general solution, as we almost always do in these Coulomb problems or so on, right? To get to the Coulomb's law, we do something like that, and I will start off with that assumption. So the equation I had as before was this equals d is constant. I have assumed that d and v both of these are constant. Minus v, correct? So, and as I said earlier, you can switch v as plus v at one. All it will do is it will. So this term we will see it later. All it does is changes the position of the mean of this distribution, and we'll come to that. Okay, so what you can notice straight up is that you have something like this. T is some positive number, and then x is in minus infinity. So the immediate thing it suggests, looking at all these partial derivatives, is obviously the transform. So the first transform I will take will be for time, and that will be a Laplace transform, looking at this 0 less than t and so on. 0 to infinity, that's where t goes from. And so what I will say, I will call the Laplace transform of p as q, okay, and so I will have p of x, and the I will write right. Okay, that's the convention I'm using for now. And so this is just a simple Laplace transform, and so that will look as s times q of s minus the initial and that is just a delta function, right? And I will write it as x comma s. Sorry. Yeah, x comma s minus initially we have a delta function, so here we get delta of x minus x naught, and this is all. This is just simply unaffected by this, except we replace these p with capital P. I don't know why I'm using so many p's and q's for that. Okay. Q or del x square is v del q over del x. And now I can do the same thing. Take the Fourier transform for this, and again the convention will be as follows. I will call this q tilde of q comma s will be 1 over 2 pi. I will use the 2 pi right away. E raised to it doesn't matter, you can use dk times q of q of x comma. Right, this is the convention. Although I'll have to probably erase this, it's good to just remember that this is what I have done. I'll just erase it. So now this time the Fourier transform doesn't affect any of this. This stays as s times. Or okay, should I even do that? Okay, no, I will just rearrange this a bit. Okay. I want to keep delta on the positive side, so I will rewrite this as delta of x minus x naught is equal to v. I'll just write it shorthand this way, minus b my plus s of s times q, right? Q tilde by definition is function of q. I won't write that element. Okay, so we can directly fill in these q tildes in terms of q, and again, right? And so I can write delta of x minus x naught as simply e raised to I k. And again, I can bring out all these partials. I can bring them out, and I can write q tilde also. V plus s times q of x comma s d over 2. This is how I have written q tilde. Sorry, this was q minus q. So simply q. I will take in the plus this q, right? Okay, and I can operate this on this immediately. So this will be ik okay. So that will give me ik v plus k squared d plus s doesn't do anything, e raised to I k. Correct? And now I can simply compare the integrand. So I will get e raised to minus I k x naught is equivalent to e raised to I k, and of course I forgot this is not x comma, this will be k comma. 2 tilde of k comma s plus k square d plus s, and d is not the differential operator. I often get confused. D is just the diffusion. Okay, and so we have straight up got this q tilde. And where is this part? So we get e raised to minus I k x naught over I k v plus k square d plus s. And now we just go ahead and invert these transforms that we have taken. It will be easier to start off with the inverse Laplace transform, and the reason is that it's of the form something into 1 over s plus a, right? And So I'll define this new function, which is the inverse Laplace transform for this, and we'll call it some what will go. What will go? You something like this. I'm running out of imagination. Anyway, so we get back this, and 1 over s plus a goes to something like the exponential, correct? And so this will be e raised to minus. This is just a constant. We don't care. And this will be e raised to minus ikv plus dk square t. Correct? Yeah, I think that's it. So, and now I just have to invert the Fourier transform. Okay? And I invert the Fourier transform once more, I will get back p straight up. Right? So I will get p of x comma t is again e raised to ikx over 2 pi as we had. I think by mistake I may have used the opposite convention the second time I wrote things, but I mean apologies for that. But I am using that. It's still consistent with what I had just used before. Just used while uh, comparing, getting the q tilde and comparing it. So I think it's consistent with that, considering the 2 pi. Yeah, I think it's consistent with that. So from minus infinity to infinity, e raised to minus ik x naught, e raised to minus ikv minus dk square t. Right? I'll just write down that. E raised to minus ikv. Yeah. And so first thing I do is I take that x minus x naught instead. So I can write this as, I'll do this on the side. E raised to I k x minus x naught minus. Now probably you are able to see why I said that the v term only decides which direction the mean goes. So ultimately all you care about is what external velocity is there. And you put that v here. And so the mean moves in that direction. I think you can see that now. Because you have something like x minus vt. Anyways, and here we have minus dk square t. Okay. And now we simply complete the what do you call the square, complete the square. So I want this minus to be here, so I will write it as plus. Okay. So dk square comes out anything. Oh sorry, dt comes out dt and k square minus ik x minus x naught minus dt over dt, correct? And to complete the square of this, I think I will have to write this as k minus I times bad handwriting. Correct? 3 2 multiplying. And so, right? And so then I have to add another factor. We will continue that. So what comes out from there is going to be e raised to, so 2 dt squared is 1 over 4 dt and 4 d square t square, that cancels with that. So we get 2 minus x minus x naught minus dt square by 4 dt, right? And that comes out of the integral and over 2 pi of course, and e raised to minus infinity to infinity minus dt k minus square dk. I forgot dk. And this is just a simple Gaussian integral, and that will get pi root pi over dt. Correct? Or is it twice that? Yeah, it's this, and I'll erase off this part. Oh. So we have e raised to minus x minus not minus dt square over 4 dt over 2 pi times this is simply pi over dt. Correct? And so finally we get this as p of equals uh, yeah. So this is what we were looking for, right? And some remarks about this. Again, I said it probably twice, but I think this is the best part about it. The peak of this Gaussian, it moves in the direction of v, and v has no other role to play apart from simply shifting this Gaussian front and back. What is important though is this d over here. So you write the general form of the Gaussian as something like this, right? Mu square over 2 and 2 pi times sigma, correct? And that means that we can compare coefficients and we'll see that sigma square is 2d. So this is again probably commonly known to you, but this is characteristic of diffusive motion. The mean square displacement is proportional to the time, and so it goes as the displacements are of the form 1 over root 1 in are of the form root t, right? And again you can say it's proportional to d, so larger the d, quicker everything is correct. But okay, so now we can go back and do that Green's function sort of thing, because okay, I should leave this off, because this p right now is a solution to the equation. It was, what was it, del p d del p. Yeah, with the boundary condition that p of x comma 0 equals delta. So it turns out that, so this is very characteristic of a Green's function type of solution, and so we can simply go ahead and do the standard thing that we do, right? So in general I write for any initial condition p of x comma 0, which is not necessarily the delta function, any general initial condition, I write that as two minus that, right? Yeah. And so you have the times p of x. Sorry, p of x and comma 0. Right? So that's the most general solution for the one-dimensional problem. But again, as I said, that it will not be too tough to comment on what would happen in general for some n number of dimensions, because the functional form should essentially stay the same, shouldn't it? Because if I have these independent axes x1, x2, I have some say n-dimensional space where you have something like this. Where the position vector is something like this, and each of these some orthogonal coordinate systems. These are n different dimensions. So in each of these, the diffusion should not the form of the diffusion equation should not change, because what happens in one dimension is entirely independent of what's happening in the other, right? And so if I again rewrite the solution we just had, where yes, this was the solution we just had. There is no reason why we can't simply go on multiplying of these individual ones for each of these xi's, and d may not even have to be the same for all. So it could be a sort of anisotropic medium, but then yeah, that's true. D will have to be constant for each separate coordinate in order to even have this sort of solution, because remember again we have taken D and V to be constant, and same thing D and V, so V may be in some arbitrary direction, but it should necessarily be a constant, because then you can decompose V into its components along each of these xi's, and I will call V dot xj equal to V. I will define this. Vj is in this fashion, and so in this manner, and D for the jth, so you can have this diffusivity tensor or something like that, but for now, for simplicity, I will write dj as the diffusion coefficient for the jth direction, and then we can go ahead and just write p of this vector x. I have written it as r, but I could write it as x. Vector p of comma t as a product of all these individual e raised to minus x minus x naught. So this will be xj minus xj naught. Naught I will write as the superscript minus vj t over 4 times djt over again the normalization 4 pi djt, and there is no reason why we can't do the same whole green function sort of thing again, and so this will be an integral over the whole volume. So I am assuming this dxj ends up in the product somehow. So this whole thing is part of the product. dxj, this will be a volume, and times p of xj. Okay, no, sorry. dxj naught p of x naught. That should be the appropriate. X again, x naught with the superscript. I couldn't introduce it, but yeah. So this is the general solution. This should be solution for n dimension. Yeah. And so I think briefly we have covered a bit of what goes on with the diffusion equation. Other things that you could explore with this diffusion equation, one would be whether there are other forms of writing J, because we have it's a vast, it's still a big simplification to simply write something like this. Although it's slightly more than fixed, it's still not the most general thing that it can do. So you could potentially explore what happens with you make better or more messier the amount of more messier models for this J, and then you could look at what happens. And yeah, there are a few other things that you could probably use a simulator and look at how these things go, but I will not be able to do that right now because I don't know how to use simulators and such things. But anyways, it is something that one could try. And this V is a constant. Again, reminding you of that. But anyways, that's all I will be saying about this diffusion. So thank you.